Welcome to day 2 of Parametric Equations. Today we're going to do a number of things with parametric equations, and the first we're going to do is to transform parametric equations to rectangular form. If you need to do this, there are two parts you have to remember. First of all, you're going to combine the x and the y equations in a way to eliminate t, and after you do that, you're going to look to see if there are any restrictions on the domain and range based upon the original function and how it was defined. So here's an example. Suppose you've got this parametric equation and you would like to rewrite it in rectangular form. So first you need to combine them somehow and eliminate the t. If we rewrite the top equation by squaring both sides, we can substitute x squared into the bottom equation. And if we do that, we have y equals 1/2 x squared plus 1. Looks like we have a parabola. But this function is limited because it's only defined when t is greater than or equal to 0. And that's because there is a square root of t in the x part of the equation. That means that x can only be greater than or equal 0 as well. And if we only plug positive or 0 numbers into the parabola equation, we're only going to get half a parabola. The restriction is that x is greater than or equal to 0. And the moral of the story is, look for restrictions. Here's what this one's going to look like. All right, well, what happens if we have something like this? Now it's harder to isolate t because t is the argument in the cosine and the sine part of the equations. But I can very cleverly square both sides of both equations. And if I do so, I get this. And now I'm happy because I'm seeing a sine squared of t and a cosine squared of t, and I know something I can do with those. First, I need to do a little reorganizing, and then I'm going to add the two equations. And there it is, cosine squared of t plus sine squared of t. Of course, I know that's the Pythagorean identity. And I've got what looks like an ellipse. So I've got to check for restrictions. Now, if you look back at the original equation, notice there was a restriction on t. It only takes on values equal to or between 0 and pi. And if you only do that, you're only going to get half of an ellipse. And this is what it looks like. So our restriction is on the range. Y can only take on values between 0 and 2 inclusive. All right, here's one for you to try. All right, well, just like a minute ago, I'm going to square both the top and the bottom equations. I'm going to reorganize a little bit. I'm going to add the equations. I notice that cosine squared of t plus sine squared of t equals 1, and I have another ellipse. This time, though, my domain restrictions on t are that t is between pi and 2 pi inclusive. So what's the restriction I need on my new equation, my ellipse equation, the one that's in a big square? Well, it turns out I need to restrict y to the values between -4 and 0. This is what this curve looks like. All right, well, here's something different. What if I want to write this parametric equation in rectangular form? Remember, I want to try to get rid of the t, so my strategy is going to be to isolate t in the top equation. So first off, I subtract x sub 1 from both sides, and then I divide both sides by x sub 2 minus x sub 1, and that equals t. Now that I've got t isolated, I can use substitution, and there's the equation rewritten. All right, well, from here, I moved the y sub 1 to the left, and I shifted things around on the right a little bit, because I noticed that y sub 2 minus y sub 1 over x sub 2 minus x sub 1 looked really familiar. In fact, if you're thinking slope, you are correct. Really what I've got here is just the equation of a line. So the equation I asked you to transform is just the general form of a line in parametric form. So let's use it. Let's suppose I want to write the equation of the line that passes through these 2 points, and I want to do it in parametric form. Well, if I've got the general form here, I can just plug the numbers in. I'm going to suggest that the first point, the one that's 2, 3, is going to be my point 1. So 2 will be my x sub 1 and 3 will be my y sub 1. And then the negative 1, 5 is my x sub 2 and my y sub 2. So I'm plugging in the numbers. I just do the arithmetic, and I end up with my equation. You'll notice from that equation, you can tell one point is at 2, 3, because if t equals 0, you get 2, 3, the first one. And then if you put a 1 in for t, you get the second point. So it's pretty intuitive. All right, you try. Find the equation of the line that passes through the points 6, 1 and 7, negative 3, and do it in parametric form. All right, well, first I just substituted the numbers in, and then I did a little arithmetic. And there's my equation. All right, now here's another one. I want to put this into rectangular form. So here's my parametric situation. Instead of sine and cosine, this time I have secant and tangent. I do have some identities I can use, though, with secant and tangent if I square them. So I'm going to follow the same strategy I did a minute ago. First off, I'm subtracting the h. The y should have a k being subtracted. There it is. Then I squared both the top and the bottom equations. And just like I did when we were working with the sine squared and the cosine squared of t earlier, I'm going to reorganize a little bit. Now if I add, I'm going to end up with secant squared t plus tangent squared t, and that is not an identity I know. But I do know secant squared t minus tangent squared t. So if I subtract, I'm going to get 1. And that is the equation of a hyperbola. All right, so now that we know that we can go from parametric to rectangular form, let's say we want to go the other direction. We have an equation in rectangular form, something like y equals 36 minus x squared, which is just a parabola. And I'd like to write it in parametric form. So the first thing I do is I just say, okay, I need to write x in terms of t. And I get to pick whatever I want. So let's just say t. That's a pretty easy one. Then if I substitute the t in where x is in the equation, I get y equals 36 minus t squared. That's it. Done. All right, you try. Well, if you decided to let x equal t, that's a good choice. And then you sub it in, you get y equals 6t plus 2. And that would be the parametric form for the equation. Now, it turns out that there are other things you could substitute in for x if you wanted. For example, you could let x equal t plus 1, or t minus 3, or t plus or minus anything you want. And you will get an equation. It'll look a little different, but it's still going to work as far as generating all the points on the line y equals 6x plus 2. And if you want to see how that works, I set up a table here. So the first column is just values that I arbitrarily picked for t. I picked a -1, 0, and a +1 because generally those are the 3 different types you need to be concerned about. And then my first attempt at rewriting the equation in parametric form, I let x equal t, and y ended up 6t plus 2. So I tried plugging some numbers in, and you can see what I got in the table. And then I tried the x equals t plus 1, which turned out to y equals 6t plus 8. And you're going to notice there are no restrictions on t. Eventually, I'm going to generate all the same points. They're staggered by 1, but I'm going to get all of them. I'm going to get the same line. All right, well, what if I decided to let x equal t to the third power? Would that work? Well, if I did that, then y would equal 6t to the third plus 2. And here's what the table would look like. I put some numbers in for t. And you'll notice when I put a -1 in for t, I actually got the same point both times. And when I put a 0 in for t, I got the same point both times. And when I put an 8 in for t, in the first equation, I got the point that I get when I put a 2 in for t in the second. But eventually I will generate all the points, the negatives, 0, positives, I'll get them all. So that works. Okay, well, what if I did x equals t squared? Well, in that case, y would equal 6t squared plus 2. And here's the table I get with that. All right, so I certainly can generate some of the same points because you can see I get 0, 2 in both of them. I also get 426 in both of them. But there is no way that I can get -1, -4 from the equation that has the squared value for t. And that's because I've got all positive numbers in the equation for y, and if I square a negative, it still ends up positive. There's no way I can generate a negative y value. So I have to be careful of the values I choose for t, for x. I can't just use anything, even though I often have a lot of things that I can choose. All right, so that's it for my presentation today. If you go into today's Schoology folder, you are going to find a file called Chapter 9, Section 5 Parametrics Pepper Book. And in that, there's a whole explanation of parametrics that's, I think, better than your book, which is why I've given it to you. And there's some problems I would like you to do. There's also a file in that same folder that has the answers to the odd problems, and number 19 and 33 are odd problems. So if you want to check your answers after you've tried the problems, you can do that. I would like you to complete these problems and put them in Schoology so that I can take a look at them before we meet again. And that's it for today's lesson. So have fun doing the problems, and I will see you on, we don't meet Wednesday because we have an asynchronous Wednesday, so I will see you on Thursday. Have a good day.